Hi students, Professor Nugent here. This is part 2 of proving the Gauss Markov Theorem. In the last video, we identified the variance of beta 1 tilde and beta 1 hat. Now we're going to take the difference and show that the difference is non-negative. So the variance of beta 1 tilde is the sum from I equals 110 of w1i squared times sigma squared. The variance of beta 1 hat is sigma squared over the sum from I equals 1 to n of r1i hat squared. Now we can pull out the sigma squared from both of these terms. They are not part of the summation, right? Sigma is not indexed over I. So we can pull sigma out of both of these terms. And we're really just trying to identify that this difference is non-negative, right? That the variance of beta 1 tilde is greater than the variance of beta 1 hat. So we only care about the difference. So we can just wipe that off the mat. We don't care about it anymore because we only care about the difference. And then what we can do is substitute in sum from I equals 1 to n of w1i r1i hat equals 1. We can substitute this thing in up here, and actually what we're going to do is substitute in this, right? Because even if we square that term, squaring that term is still going to be equal to 1. So we're going to substitute this into the numerator up here so that we have sum from I equals 1 to n of w1i minus sum from I equals 1 to n w1i r1i hat squared over sum from I, in parentheses, that whole thing is squared, sum from I equals 1, I equals 1 to n r1i hat squared. Good. Now that we have this expression, we can write this expression as the sum from I equals 1 to n of w1i minus gamma 1 times r1i, gamma 1 hat, r1i hat squared, where gamma 1 hat is equal to sum from I equals 1 to n of w1i r1i hat all over sum from I equals 1 to n of r1i hat squared. So observe that what you have here, this is the sum of squared residuals of a simple regression of w1i on r1i hat, right? Because this gamma 1 hat is the coefficient in that simple regression, as we have from this expression here. Just like our expression of beta 1 hat, this is the sum from I equals 1 to n of w1i r1i hat over the sum from I equals 1 to n of r1i hat squared. So this is going to be non-negative unless we can perfectly predict w1i using r1i hat, which is not a reasonable expectation. So this is going to be non-negative. What I'd like to do is to show that this line gives us this line, okay? Because this completes our proof. But how do we get from here to here is the question. But this completes our proof because, again, unless the partial out part of x1 perfectly predicts this function of all of the variables, which is not a reasonable expectation, that's not, this is very unlikely, then we're going to have residuals, and as long as you have residuals, that's going to be non-negative. So let's show that this line gives you this line. I want to get from here to here. How did we do that? This is going to get kind of big. So this is equal to the sum from I equals 1 to n, and we're going to factor this out. This is w1i squared minus sum from I equals 1 to n of W1I R1I all over sum from I equals 1 to n of R1I hat squared times R1I hat squared. Right, so we just plugged in the expression for gamma 1 hat. This is equal to sum from, we don't have the squared yet. We're going to have the squared in just a moment. Squared is still on the outside. Sum from I equals 1 to n. Now let's have the squared. W1I squared minus, so we're going to multiply this times this. Basically, we're factoring out this term so that you have sum from I equals 1 to n W1I R1I over sum from I equals 1 to n R1I hat squared. Then you have R1I hat, and it's multiplied by this. That's W1I. And we're summing over this term. So notice that you have sum from I equals 1 to n of R1I, W1I, R1I. And again, sum from I equals 1 to n R1I hat W1I. So that's going to be squared. Minus the exact same term. So I'm just going to do parentheses that plus this thing squared, sum from I equals 1 to n W1I R1I all over sum from I equals 1 to n R1I. These are hats. That's squared. This is R1I hat. That's squared. We can distribute this power well, let's not distribute the power just yet. We'll distribute the power in just a moment. When we distribute the power, you're going to see that we have sum from I equals 1 to n of R1I squared over sum from I equals 1 to n of R1I squared times sum from I equals 1 to n of R1I squared. And those are going to cancel out. You're going to be left with just 1. So what you end up having is minus 1 of these terms minus another minus 2. And let's bring out our sum from I equals 1 to n. One to n R1I hat W1I. And again, sum from I equals 1 to n of R1I hat squared, squared, squared. Now some things are going to cancel. What we have is that this cancels because you have 2 of these in the denominator, 1 of them in the numerator, so that cancels. And you have, this is the same term as this, because sum from I equals 1 to n of W1I times R1I hat times sum from I equals 1 to n of R1I hat W1I. That's squared. So you have minus 2 plus 1. Minus 2 plus 1 gives you negative 1, which is what we started with. All right, so that is how we got from that second line to the first line. And that finishes all the work in the Gauss Markov theorem.